You are looking at the night sky right now. Maybe you are in your backyard. Maybe you are standing on a beach or lying in a field somewhere far from city lights. You see stars, thousands of them. And somewhere in the back of your mind, you have a story about how all of this began. It started with an explosion. You have probably heard it described this way 100 times. The universe began when all the matter in existence was compressed into a tiny, impossibly dense point. And then, bang, it blew apart. Fragments of primordial fire hurtled outward through the void, cooling and clumping into stars and galaxies, and eventually, after billions of years, into you. It is a beautiful image. It is also completely wrong. Not the part about the universe beginning. That happened. Not the part about it being impossibly hot and dense. That is true too. What is wrong is the explosion, the outward rush, the debris scattering through space. Because here is the thing nobody tells you. The Big Bang was not an explosion of matter through space. It was an expansion of space itself. And the difference between those two ideas is not just a technicality. It is the difference between understanding reality and living inside a comfortable illusion. So let me ask you this. If the Big Bang was not an explosion, what was it? Where did it happen? And why does everyone, including scientists who should know better, keep describing it wrong? Close your eyes for a moment and imagine an explosion, a bomb detonating, a star going supernova, a firework bursting in the sky. What do all of these have in common? They all happen in a specific location. There is a center point, a place where the explosion originates, and the debris flies outward from that center into the surrounding space. If you were standing nearby, you could point at where it happened. You could say, there, that is where the explosion was. This is how most people imagine the Big Bang. They picture the entire universe compressed into a point, smaller than an atom, sitting somewhere in the darkness. And then this point explodes, throwing matter outward like shrapnel from a cosmic grenade. The universe expands as this debris spreads through the pre-existing emptiness, filling the void with galaxies and stars. This mental image feels natural. It makes intuitive sense. And it is the story we have been telling ourselves for nearly a century, ever since the astronomer Edwin Hubble made a discovery that shook the foundations of human understanding. In 1929, working at the Mount Wilson Observatory in California, Hubble published one of the most important papers in the history of science. He had been studying distant galaxies using the world's most powerful telescope at the time, and he noticed something strange. Almost every galaxy he observed was moving away from us. Not just a few of them, nearly all of them. And the farther away a galaxy was, the faster it seemed to be receding. This was not entirely new information. A decade earlier, an astronomer named Vesto Slipher had already measured the light from dozens of galaxies and found that most of them showed what is called a redshift. Their light was stretched to longer wavelengths, indicating they were moving away. But Slipher did not have the tools to measure how far away these galaxies were. He could tell they were receding, but he could not connect their speed to their distance. Hubble put the pieces together. Using a type of star called a Cepheid variable, which pulses at a rate that reveals its true brightness, he calculated the distances to dozens of galaxies. When he compared those distances to Slipher's velocity measurements, a pattern emerged. It was a straight line. The farther away a galaxy was, the faster it was moving away from us. Think about what this implies. If everything is moving away from everything else, and the more distant things are moving away faster, then at some point in the past, everything must have been closer together. Run the clock backward, and the galaxies converge. Keep running it, and the entire observable universe collapses into a single point. This is the logic that gave birth to the Big Bang model. 2 years before Hubble's famous paper, in 1927, a Belgian physicist and Catholic priest named Georges Lemaître had already derived this idea mathematically. Using Einstein's equations of general relativity, Lemaitre showed that the universe could not be static. It had to be either expanding or contracting. And if it was expanding now, then in the past, it must have been smaller, denser, hotter. Lemaitre called this primordial state the primeval atom. He imagined the entire cosmos condensed into a single quantum of existence, which then fragmented and expanded to become everything we see today. The image was irresistible, a cosmic egg hatching, a primordial explosion creating the universe. When the British astronomer Fred Hoyle mockingly referred to this idea as the Big Bang during a BBC radio broadcast on March 28, 1949, he meant it as an insult. Hoyle favoured a competing theory called the steady-state model, which proposed that the universe had always existed and was continuously creating new matter to maintain a constant density. The Big Bang, he thought, was a ridiculous notion, an explosion out of nothing, a creation event that smelled suspiciously like religion masquerading as science. But the name stuck, and so did the image it evoked. A colossal detonation at the dawn of time. Here is the problem. That image is wrong. To understand what the Big Bang actually was, you need to think about space differently than you have ever thought about it before. In everyday life, space is just the emptiness between things. It is the stage on which objects exist and move. You walk through space. Light travels through space. Stars are separated by vast stretches of space. Space itself seems to be nothing, just the absence of stuff. But Einstein showed us something remarkable. Space is not nothing, it is something. Space-time, as he called it, is a real, physical entity that can bend, warp, stretch, and curve. Massive objects like stars and planets create indentations in space-time, and this curvature is what we experience as gravity. Now here is where it gets strange. If space itself can stretch, then the distances between objects can increase, not because the objects are moving through space, but because space itself is expanding. The objects are not going anywhere. They are standing still in their local patch of space-time. But the fabric of space between them is growing, like the surface of a balloon being inflated. This is what Hubble's observations actually showed. The galaxies are not flying away from us through space like debris from an explosion. They are being carried along as space itself expands. The expansion is happening everywhere, simultaneously, with no center and no edge. Picture a loaf of raisin bread baking in an oven. Before you put it in, the raisins are close together, embedded in the dough. As the bread rises, the dough expands in all directions. From the perspective of any individual raisin, every other raisin appears to be moving away. And the farther away a raisin is, the more dough there is between them, so the faster it seems to recede. But the raisins themselves are not moving through the dough. The dough itself is expanding, carrying the raisins along with it. This is a much better analogy for what is happening to the universe. The galaxies are the raisins. Space is the dough. And the expansion is not an explosion outward from a center. It is a swelling of the entire loaf. But here is the part that really twists your brain. In the raisin bread analogy, the loaf has a center. If you were a raisin, you could figure out where the middle of the bread is. The universe does not work this way. There is no center to the expansion. No special point that was the origin of the Big Bang. The Big Bang happened everywhere. Imagine you are standing on the surface of a balloon. Now imagine the balloon is being inflated. Every point on the surface is getting farther from every other point. If you put your finger on one spot and look around, you will see all the other spots moving away from you. And the same would be true if you stood on any other spot. Every point on the balloon surface thinks it is at the center of the expansion because the expansion is uniform. There is no special location. The same is true for the universe. When you look out at distant galaxies and see them receding in all directions, it is tempting to conclude that you are at the center of everything. But an observer in any one of those distant galaxies would see exactly the same thing. All galaxies receding in all directions. The expansion has no center because it is not expanding from a point. It is expanding everywhere. And this brings us to the deepest, strangest truth about the Big Bang. It was not an explosion that happened at a particular location in space. It was an expansion of space itself that happened at every location simultaneously. The Big Bang did not occur somewhere. It occurred everywhere, including right where you are sitting now. Let us go deeper, because even this corrected picture leaves something out. When cosmologists talk about the expansion of the universe, they are not just saying that galaxies are getting farther apart. They are saying something more profound. The metric of space is changing. This is technical language, but here's what it means. In physics, we measure distances using coordinates. You are 3 feet from the wall. The moon is 238,900 miles away. Alpha Centauri is 4.37 light-years distant. These measurements assume that the standard of distance, the ruler we are using to measure, stays constant. A mile is always a mile. A light-year is always a light-year. But in an expanding universe, this assumption breaks down. The ruler itself is stretching. Imagine you had a tape measure that was 1 billion light-years long, and you laid it out between 2 distant galaxy clusters. At the moment you laid it down, it might read exactly 1 billion light-years, but come back later and the tape measure has stretched. Not because anything moved, but because the space the tape measure was made of has expanded. Now it reads 1.1 billion light-years, or 2 billion, or more. This is what cosmologists mean when they say the universe is expanding. It is not that objects are flying apart through a static backdrop. The backdrop itself is growing. The fabric of reality is stretching. Charles Lineweaver, a cosmologist at the Australian National University, put it this way in a landmark 2005 paper in Scientific American titled Misconceptions about the Big Bang, co-authored with Tamara Davis. The Big Bang was not an explosion in space. It was more like an explosion of space. This distinction matters for reasons that go beyond philosophical hair-splitting. It has practical consequences that can be observed and measured. Consider the cosmic microwave background radiation, the afterglow of the Big Bang itself. In 1964, 2 radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, calibrating a sensitive microwave antenna originally designed to track satellite communications. No matter where they pointed it in the sky, they picked up a faint hiss of static. They checked everything. They cleaned out the pigeon droppings that had accumulated inside the antenna. They ruled out interference from New York City, from the galaxy, from everything they could think of. The noise would not go away, because the noise was not noise. It was the oldest light in the universe, stretched by 13.8 billion years of cosmic expansion from the hot, bright radiation of the early universe into the cool, faint glow of microwaves. Penzias and Wilson had accidentally discovered the cosmic microwave background, the thermal radiation left over from a time when the universe was only 380,000 years old and had finally cooled enough for light to travel freely. This radiation fills the entire universe. It comes from every direction, equally bright no matter where you look, and it has almost exactly the same temperature everywhere, about 2.7 degrees above absolute zero. The uniformity is stunning. Different parts of the sky that have never been in contact with each other, that are so far apart that light has not had time to travel between them in the entire history of the cosmos, somehow have the exact same temperature. If the Big Bang had been an ordinary explosion, this would make no sense. In an explosion, the debris is lumpy and chaotic. Some parts fly faster, some slower, some are hotter, some cooler. There is no mechanism to smooth everything out, no way for distant regions to communicate and equalize their temperatures. But if the Big Bang was an expansion of space itself, and if that expansion was preceded by a period of incredibly rapid growth called inflation, then the uniformity makes perfect sense. Before inflation, the tiny patch of space-time that would become our entire observable universe was so small that all its parts were in contact, able to reach a uniform temperature. Then inflation expanded that tiny uniform patch by a factor of at least 10 to the 26th power, in less than 10 to the negative 32nd of a second. Regions that had been neighbors were suddenly on opposite sides of the cosmos, but they carried with them the memory of their shared temperature. This is not speculation. In 1981, physicist Alan Guth, working at Stanford's SLAC National Accelerator Laboratory, proposed the theory of cosmic inflation to solve precisely this problem, known as the horizon problem. Inflation also explained why the universe appears to be geometrically flat, neither curving back on itself like a sphere, nor flaring outward like a saddle. Both of these puzzles, the horizon problem and the flatness problem, had bedeviled cosmologists for years. Inflation solved them both in one elegant stroke, and the evidence for inflation is written in the cosmic microwave background itself. The Planck satellite, launched by the European Space Agency, has mapped the microwave sky in exquisite detail, revealing tiny fluctuations in temperature, variations of only a few 100,000ths of a degree. These fluctuations are the seeds of all cosmic structure. They are the quantum jitters of the inflationary field, stretched by the expansion of space to cosmic scales, eventually collapsing under their own gravity to form galaxies and clusters and superclusters. The pattern of these fluctuations is exactly what inflation predicts, not what an explosion would produce, not what a steady-state universe would show. Inflation, an expansion of space itself, driven by an exotic form of energy with negative pressure, matches the data with stunning precision. But wait, if the Big Bang was not an explosion and it happened everywhere, then what do we mean when we say the universe had a beginning Does the Big Bang still mark the origin of space and time? This is where the story gets complicated, and where scientists themselves sometimes disagree. The classical Big Bang model, based on Einstein's general relativity, predicts that if you run the expansion backward, you reach a point of infinite density and infinite temperature, a singularity. At this point, all the matter and energy in the universe would be compressed into a space of zero volume. The equations break down. The mathematics gives nonsensical answers. The singularity is not a place or a moment that physics can describe. It is a sign that our theory is incomplete. For decades, physicists treated the singularity as a genuine beginning, the moment when space and time themselves came into existence. Stephen Hawking and Roger Penrose proved powerful theorems in the 1960s and 70s showing that singularities were inevitable in universes governed by general relativity. If the universe contained ordinary matter and energy, and if it was expanding, then there had to be a singularity in its past. But singularities are deeply unsatisfying. They represent the limits of our knowledge, not physical reality. No physicist truly believes that the universe was once a point of infinite density. Something must have happened at very early times that our current theories cannot capture. This is where quantum mechanics enters the story. At extremely small scales and extremely high energies, the smooth fabric of space-time described by general relativity gives way to a seething quantum foam. The usual notions of distance and duration lose their meaning. Time itself may have emerged from something more fundamental, rather than stretching back to an infinite past or beginning at a well-defined moment. Several approaches to quantum gravity, loop quantum gravity, string theory, and others suggest that the classical singularity is an artifact of incomplete physics. In loop quantum gravity, for instance, space is not continuous, but made of discrete chunks, like atoms of geometry. These chunks have a minimum size, which prevents the infinite compression of a singularity. Instead of a Big Bang, there might have been a big bounce, a previous universe that contracted, reached a minimum size, and then expanded again to become our cosmos. This is still speculative. We do not yet have a complete theory of quantum gravity, but the lesson is clear. The Big Bang, as physicists understand it today, does not necessarily mean a beginning from nothing. It means a period of extremely high temperature and density, from which our universe as we know it emerged. What came before, or whether before even has meaning, remains an open question. What we can say with confidence is this: the universe has been expanding and cooling for about 13.8 billion years. At very early times, it was unimaginably hot and dense. The patterns we observe in the cosmic microwave background and the distribution of galaxies are consistent with an early period of inflationary expansion. And the expansion itself is not galaxies flying through space, but space itself stretching between them. The Big Bang was real, but the explosion is not. You might be wondering, if space is expanding everywhere, why is Earth not expanding? Why is the Milky Way not expanding? Why are the atoms in your body not being stretched apart? The answer is that expansion only happens on scales where gravity and other forces are not holding things together. Your body is held together by electromagnetic forces between atoms. Earth is held together by gravity. The solar system is gravitationally bound to the sun. Our galaxy is a gravitationally coherent structure. Even our local group of galaxies, which includes Andromeda, due to collide with the Milky Way in about 4 billion years, is gravitationally bound. On these scales, the forces holding matter together are far stronger than the tendency of space to expand. Your atoms are not getting farther apart. Your distance from the sun is not increasing. Brooklyn is not expanding. But on cosmological scales, between galaxy clusters that are not gravitationally bound to each other, the expansion of space dominates. This is why distant galaxies are receding from us, not because they are flying through space, but because the space between us and them is growing. As Lineweaver and Davis wrote in their Scientific American article, expansion by itself produces no force. Photon wavelengths expand with the universe because, unlike atoms and cities, photons are not coherent objects whose size has been set by a compromise among forces. Light traveling through expanding space gets stretched. That is the cosmological redshift. It is different from a Doppler shift, which is caused by motion through space. The cosmological redshift is caused by the expansion of space itself. The two effects look similar but have different origins. And here is something even stranger. Because space is expanding, distant galaxies can appear to recede from us faster than the speed of light. Yes, faster than light. This sounds like it should violate special relativity, but it does not. Einstein's speed limit applies to objects moving through space. It does not apply to space itself expanding. There is no prohibition against distant regions of space receding faster than light, as long as nothing is actually traveling through the local space-time faster than light. Right now, galaxies beyond a certain distance, called the Hubble horizon, are receding from us faster than light. We will never be able to reach them, no matter how fast we travel. They are beyond our cosmic event horizon, cut off from us forever by the expansion of space. The observable universe is finite and shrinking in the sense that fewer and fewer galaxies are within our reach. This is not science fiction. This is measured fact. So why do people, even scientists, keep describing the Big Bang as an explosion? Partly, it is a matter of convenience. Explosion is a vivid word. It grabs attention. It makes for good headlines and dramatic documentaries. Saying the expansion of the metric of spacetime from an initial hot, dense state is accurate, but does not have the same punch. Partly, it is a failure of communication. When scientists first developed these ideas in the early 20th century, they themselves used metaphors that were not quite right. Lemaitre called his initial state the primeval atom and described its evolution as a kind of radioactive decay or fragmentation, images that evoke an explosion. The name Big Bang itself, coined as a dismissive joke by Hoyle, reinforced the misconception. And partly it is because the correct picture is genuinely hard to visualize. We live in space. We move through space. We experience space as the arena for events, not as an entity that can stretch and expand. The idea that the universe has no center, that the Big Bang happened everywhere simultaneously, that space itself is the thing that is growing. These concepts run counter to every intuition we have developed navigating the everyday world. But this is precisely what makes the truth so remarkable. The universe is not what it appears to be. The comfortable, intuitive picture you have in your head is a simplification, a model that works fine for everyday purposes, but collapses when you try to apply it to the cosmos as a whole. The real universe is weirder, more subtle, and more beautiful than any explosion could be. To truly appreciate the revolution we have been describing, you need to meet the people who made it possible. Not as names in a textbook, but as human beings grappling with ideas that would reshape our understanding of existence. Georges Lemaître was born in Charleroi, Belgium, in 1894. He studied engineering at the Catholic University of Louvain, but his education was interrupted by the First World War. He served as an artillery officer in the Belgian army and witnessed the first poison gas attack in history. After the war, he returned to his studies, but something had changed. He pursued both physics and theology, eventually becoming a Catholic priest in 1923. Lemaitre was not content to accept the prevailing view that the universe was static and eternal. When he studied Einstein's equations of general relativity, he saw what Einstein himself had tried to avoid. The mathematics pointed to a universe in motion. In 1927, Lemaitre published a paper in an obscure Belgian journal arguing that the universe was expanding. He even calculated the rate of expansion, what we now call the Hubble constant, 2 years before Hubble's famous paper. But Lemaitre did not stop there. In 1931, he proposed something even more radical. The entire universe had emerged from a single primeval atom, a quantum of existence that had fragmented and expanded to become everything we see. This was the first scientific formulation of what we now call the Big Bang. Einstein initially rejected Lemaitre's ideas. When the two men met at a conference in 1927, Einstein reportedly told him, "Your calculations are correct, but your physics is abominable." Einstein preferred a static universe and had even modified his own equations with a cosmological constant to prevent them from predicting expansion. But Lemaitre persisted. By 1933, when Einstein heard Lemaitre present his theory at the California Institute of Technology, his attitude had changed. Einstein stood and applauded, reportedly calling it the most beautiful and satisfactory explanation of creation to which I have ever listened. Lemaitre was careful to separate his science from his faith. He insisted that his theory had no theological implications, that it was a physical hypothesis to be tested against observations, not a scientific proof of creation. "As far as I see," he wrote, "such a theory remains entirely outside any metaphysical or religious question. It leaves the materialist free to deny any transcendental being." This was important. The Big Bang theory was initially viewed with suspicion by some scientists precisely because it seemed to invoke a moment of creation. Fred Hoyle's steady-state theory was partly motivated by a desire to avoid this implication, but Lemaitre understood that science operates within its own domain. Physics can describe how the universe evolved from an initial state. It cannot tell us why that state existed or whether it was created by a deity. Then there was Alan Guth, the physicist who revolutionized our understanding of the very early universe. Guth was not a cosmologist by training. He was a particle physicist interested in the esoteric mathematics of grand unified theories and magnetic monopoles. It was only by accident that he stumbled onto the idea that would make him famous. In 1978, Guth attended a lecture by physicist Robert Dicke at Cornell University. Dicke explained the flatness problem, the mystery of why the universe appears to have almost exactly the critical density needed for flat geometry. Any deviation from flatness in the early universe should have grown over time, making the universe either obviously closed or obviously open. Yet observations showed the universe was very close to flat, Guth did not immediately grasp the significance of this puzzle. But a year later, working at the Stanford Linear Accelerator Center, he was trying to understand why magnetic monopoles, particles predicted by grand unified theories, had never been observed. He realized that if the early universe had undergone a period of exponential expansion, monopoles produced before this expansion would be diluted to undetectable levels. Then came the breakthrough. On December 6, 1979, Guth was working through the equations at home, trying to understand the cosmological implications of his monopole solution. As he later recounted, I discovered that this incredible expansion would also solve the flatness problem. He wrote in his notebook, in capital letters, "Spectacular realization." Guth understood that he had found something profound. The same mechanism that explained the monopole problem also explained why the universe was flat and why the cosmic microwave background was so uniform. Inflation solved multiple puzzles with a single elegant idea. He published his findings in January 1981 in a paper titled Inflationary Universe, a possible solution to the horizon and flatness problems. It has since been cited about 13,000 times. The theory was not perfect. Guth's original version had problems. The universe would have remained in an inflationary state forever, never transitioning to the hot Big Bang. But within a few years, physicists like Andre Linde at Stanford and Paul Steinhardt and Andreas Albrecht at the University of Pennsylvania developed improved versions that avoided these difficulties. Inflation is now considered a cornerstone of modern cosmology. It explains observations that the classical Big Bang model cannot, and it fundamentally changes our picture of the early universe, from an explosion out of nothing to a quantum phase transition that created the conditions for the hot Big Bang. When the universe was young, less than 380,000 years old, it was so hot that atoms could not exist. Electrons were stripped from atomic nuclei, creating a plasma that scattered light like fog scatters a flashlight beam. The universe was opaque. Light could not travel freely. It was constantly absorbed and re-emitted by the charged particles filling space. Then something remarkable happened. The universe cooled enough for electrons to bind with protons, forming neutral hydrogen atoms. This transition, called recombination, was like the fog suddenly lifting. Light was set free. Photons that had been bouncing around for hundreds of thousands of years suddenly found themselves in a transparent universe. They streamed outward in all directions, carrying information about the state of the cosmos at that moment. Those photons have been traveling ever since. Over 13.8 billion years, the expansion of space has stretched their wavelengths by a factor of about 1 to 100. What was once visible light, the glow of a hot plasma, is now microwave radiation with a temperature of 2.7 to 25 Kelvin, just a few degrees above absolute zero. This is the cosmic microwave background. It surrounds us. It fills the universe. It is the oldest light we can ever see, and it is not perfectly uniform. When the COBE satellite first mapped the microwave sky in the early 1990s, it revealed tiny temperature fluctuations, variations of about 1 part in 100,000. These fluctuations were incredibly small, but they were there. They were the seeds of all cosmic structure. The physics of these fluctuations is beautifully understood. Before recombination, the plasma that filled the universe was not quite uniform. Slightly denser regions had slightly stronger gravity, pulling in more matter, but the radiation pressure in the plasma resisted this compression. The result was acoustic oscillations, sound waves propagating through the early universe at about half the speed of light. These oscillations left characteristic patterns in the cosmic microwave background. Regions that were at maximum compression when recombination occurred appear slightly hotter. Regions at maximum rarefaction appear slightly cooler. The size of the oscillations depends on how far sound could travel before recombination, a distance that depends on the contents and geometry of the universe. By measuring these patterns, cosmologists can determine the composition of the universe with extraordinary precision. The Planck satellite, which observed the microwave sky from 2009 to 2013, found that the universe is 68.3% dark energy, 26.8% dark matter, and only 4.9% ordinary matter. It found that the universe is geometrically flat to within 0.4%. It found that the age of the universe is 13.799 plus or minus 0.001 billion years. These are not guesses, they are measurements. They come from fitting detailed models of the early universe to the observed patterns in the cosmic microwave background. The agreement between theory and observation is stunning, one of the great achievements of modern science. And none of this would make sense if the Big Bang were an explosion. In an explosion, there is no mechanism to produce acoustic oscillations. There is no plasma, no recombination, no release of photons from a last scattering surface. The cosmic microwave background is evidence for a hot, dense, uniform early universe. Exactly what the Big Bang model predicts. Here is something that may keep you up at night. The fluctuations in the cosmic microwave background, the seeds of galaxies, the origins of all cosmic structure, began as quantum fluctuations. They were random jitters in the fields that filled the early universe, amplified by inflation to cosmic scales. Quantum mechanics tells us that empty space is not truly empty. Even in a perfect vacuum, pairs of particles and antiparticles constantly pop into existence and annihilate each other. Fields fluctuate around their average values. There is an irreducible fuzziness to reality at the smallest scales. During inflation, these quantum fluctuations were stretched along with space itself. A fluctuation that began at subatomic scales was blown up to astronomical scales, frozen into place as the exponential expansion carried it beyond the horizon. When inflation ended, these fluctuations became density perturbations in the hot plasma, slightly denser and slightly less dense regions that would eventually grow into galaxies and voids. This means that the entire large-scale structure of the universe, the distribution of galaxies, the cosmic web of filaments and voids, the clusters and superclusters that span hundreds of millions of light years, all of it traces back to quantum uncertainty. The universe we see is, in a very real sense, a quantum phenomenon writ large. There is something almost absurd about this. Quantum mechanics is the physics of the very small, the realm of atoms and particles and probabilities. Cosmology is the physics of the very large, the realm of galaxies and universes and billions of light years. Yet inflation connects them. The same quantum principles that govern the behavior of electrons govern the distribution of matter across the cosmos. This is why physicists say that inflation provides a mechanism for the origin of structure. It does not just explain why the universe is uniform on large scales or flat. It explains why there are galaxies at all. Without quantum fluctuations amplified by inflation, the universe would be perfectly smooth, perfectly uniform, perfectly boring. There would be no stars, no planets, no life, no one to wonder where it all came from. You exist because of quantum uncertainty. The galaxy you live in exists because of quantum uncertainty. The vastness of the cosmos, in all its complexity and beauty, is the quantum foam of the early universe, frozen and amplified and grown over 13.8 billion years. This is not philosophy. This is measured fact. The pattern of fluctuations in the cosmic microwave background matches the predictions of inflationary models with quantum initial conditions. The statistical properties of the temperature variations, their amplitude, their scale dependence, their distribution, all agree with what quantum field theory predicts. We are quantum beings in a quantum cosmos. Here is a question that often trips people up. How can the universe be 13.8 billion years old if we can see objects 46 billion light years away? If the Big Bang were an explosion, this would make no sense. Light travels at a fixed speed. In 13.8 billion years, it should have traveled 13.8 billion light years, no more. The observable universe should have a radius of 13.8 billion light years. But the universe is not static. Space is expanding. Light that set off toward us 13.8 billion years ago has been traveling through space that was continuously stretching. By the time the light reaches us, the object that emitted it is much farther away than when the light began its journey. The co-moving distance to the edge of the observable universe, the distance you would measure if you could somehow pause the expansion, is about 46 billion light years in every direction. The diameter of the observable universe is roughly 93 billion light years. This is much larger than 13.8 billion light years, because space has been expanding the entire time the light was in transit. And the observable universe is not the whole universe. It is just the part whose light has had time to reach us. Beyond that horizon, there is more universe, possibly much more, possibly infinitely more. We cannot see it. We cannot interact with it. But there is no reason to think space ends at our observational limit. If inflation lasted long enough, the total universe could be inconceivably larger than the observable part. Some calculations suggest it could be 10 to the 23rd power times larger, or 10 to the 100th power, or even infinitely larger. Our observable universe, everything we have ever seen, everything we will ever see, could be a vanishingly small bubble in an incomprehensibly vast cosmos. This is humbling, and it is another reason why the explosion picture fails. In an explosion, there is a center and an edge. The debris has limits. The blast radius is finite. But in an expanding universe, especially one that underwent inflation, there may be no limits at all. The universe is not expanding into anything. There is no outside. There is no boundary. There is just more and more space, possibly without end. If the universe has been expanding for 13.8 billion years, what happens next? For most of the 20th century, cosmologists assumed that the expansion would gradually slow down. Gravity, after all, pulls matter together. The combined gravitational attraction of all the galaxies should act as a cosmic brake, decelerating the expansion over time. The question was whether gravity would eventually halt the expansion, causing the universe to collapse in a big crunch, or whether the expansion would slow but never quite stop, continuing forever at an ever-decreasing rate. In 1998, two teams of astronomers set out to measure the deceleration by studying distant supernovae. Type Ic supernovae are excellent cosmic distance markers because they all have approximately the same intrinsic brightness. By comparing how bright they appear to how bright they should be, You can calculate how far away they are, and by measuring their redshifts, you can determine how fast the universe was expanding when they exploded. The results were shocking. The expansion was not slowing down, it was speeding up. Something was pushing the universe apart, counteracting gravity, accelerating the expansion. Cosmologists called it dark energy. We still do not know what it is. It could be the cosmological constant, a constant energy density of empty space, which Einstein had introduced and then abandoned, calling it his biggest blunder. It could be a dynamic field, like quintessence, whose energy density changes over time. It could be something else entirely, something beyond our current physics. What we do know is that dark energy comprises about 68% of the total energy content of the universe. Dark matter makes up about 27%. Ordinary matter, the atoms that make up stars and planets and people, is only about 5%. We live in a universe dominated by mysterious components we cannot directly see or touch. If dark energy continues to drive accelerated expansion, the fate of the universe is bleak. Galaxies beyond our local group will recede faster and faster, eventually crossing the cosmic event horizon and vanishing from view forever. The night sky will gradually empty. The local group will merge into a single galaxy, isolated in an ever-expanding void. Stars will burn out. Black holes will evaporate through Hawking radiation over unimaginable timescales. The universe will approach a state of maximum entropy, a cold, dark, empty expanse with nothing happening, forever. This is sometimes called the heat death of the universe. It is the ultimate consequence of the second law of thermodynamics, applied to cosmological scales. But this is not certain. Dark energy might not be constant. It could decay. It could change. The universe could undergo another phase transition, as it did during inflation. New physics could intervene. The ultimate fate remains unknown. What is certain is that the expansion continues. Space keeps stretching. Distant galaxies keep receding. The universe is not static, not stable, not eternal in the form we know. It is dynamic, evolving, changing, not exploding outward, but unfolding in ways we are only beginning to understand. For all the triumphs of modern cosmology, there is much we do not understand. We do not know what dark matter is. We know it exists because we can see its gravitational effects on galaxies and clusters and the cosmic microwave background, but we have never detected a dark matter particle in a laboratory. We do not know if it is made of weakly interacting massive particles, axions, primordial black holes, or something else entirely. Decades of searches have come up empty. We do not know what dark energy is. We know it is causing the expansion of the universe to accelerate, but we do not know why. The simplest explanation, that dark energy is the cosmological constant, a constant energy density of empty space, requires a value that is inexplicably small. According to quantum field theory, the vacuum should have a much higher energy density than we observe. This discrepancy, sometimes called the cosmological constant problem, has been called the worst prediction in the history of physics. We do not know whether inflation actually happened. The evidence is strong, the flatness, the uniformity, the pattern of fluctuations, but it is circumstantial. We have not detected the gravitational waves that inflation should have produced, the primordial ripples in space-time that would provide smoking gun evidence. Several experiments are searching for these waves, but so far, nothing definitive has been found. We do not know what happened at the very beginning. Inflation pushes the classical singularity into the past, but it does not eliminate it entirely. Some theories propose that inflation is eternal, that most of space is always inflating, with occasional bubbles like our universe nucleating within it. Others propose that our universe emerged from a previous universe through a bounce. Others invoke the multiverse, string theory, quantum cosmology. None of these ideas has been tested. None may ever be testable. And we do not know what the universe ultimately is. Is it finite or infinite? Is it one of many? Is space-time fundamental, or does it emerge from something deeper? Is consciousness relevant to cosmology, or is it just a byproduct of complex arrangements of matter? These questions lie at the boundary of science and philosophy, and they may remain there for a long time. But this is what makes cosmology so compelling. It is not a finished edifice. It is a work in progress. Every answer raises new questions. Every discovery reveals new mysteries. The Big Bang was not an explosion. That much we know. But what it was, what the universe is, remains in many ways an open question. And that is the most exciting thing of all. And now let me tell you why this matters to you. Not to the abstract project of understanding cosmology, but to you personally, reading these words right now. Because the misconception of the Big Bang as an explosion is not just a technical error. It distorts something fundamental about our place in the universe. If the Big Bang were an explosion, there would be a center, a special place, a location where everything began, where matter first burst into existence and flew outward. The rest of the universe would be defined in relation to that center, closer or farther, older or younger in some sense. There would be a direction to history, a geometry of importance. But there is no center. There is no edge. There is no special place. The Big Bang happened right where you are sitting, in the exact same way it happened everywhere else. You are at the center of the universe, and so is every other point, and so is every other observer who will ever exist. This is not a mystical statement. It is a straightforward consequence of the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, looking the same in every direction and from every location. This assumption is not philosophical wishful thinking. It is supported by the cosmic microwave background, which is uniform to 1 part in 100,000. It is supported by the distribution of galaxies, which shows no preferred direction or center. The universe really is the same everywhere, and this means something profound. You are not at the edge of creation, looking back towards some distant origin. You are embedded in the same cosmic fabric that constitutes the most distant quasars. The light from those quasars has been traveling for billions of years, stretched by the expansion of space, carrying information about conditions when the universe was young. But the space through which that light traveled is continuous with the space around you. There is no boundary, no separation, no difference in kind. The Big Bang did not happen long ago and far away. It is happening now, here, in the ongoing expansion of space between gravitationally unbound structures. The cosmic microwave background bathes you right now in the afterglow of the primordial fireball. You are inside the Big Bang. You always have been. There is a line from the astronomer Carl Sagan that has become almost a cliché. We are made of star stuff. It is true. The carbon in your cells, the oxygen you breathe, the iron in your blood, All of it was forged in the hearts of massive stars that exploded billions of years ago. You are literally made of stellar debris. But there is a deeper truth beneath this one. You are not just made of star stuff. You are made of space-time itself. The atoms in your body exist within the fabric of space. Your consciousness, whatever it is, unfolds in time. You are a localized knot in the cosmic tapestry, a temporary concentration of matter and energy in the eternal expansion of the universe. And that universe did not begin with an explosion. It began with something we do not have a good word for, an unfolding, an emergence, a stretching of existence itself. What then? Was the Big Bang really? It was a state of affairs, an initial condition, a moment when the observable universe was infinitely denser and hotter than it is today, or at least so dense and hot that our current physics cannot describe it. From that state, space began expanding. Matter and energy cooled. Protons and neutrons formed, then atomic nuclei, then atoms. Light broke free of the opaque plasma and streamed in all directions, eventually to be detected by radio astronomers in New Jersey. Stars ignited, lived, died, and scattered heavy elements into space. Those elements coalesced into planets, and on at least one planet, into living things that eventually looked up at the night sky and wondered where it all came from. This is the story told by Cosmology. It is supported by mountains of evidence: the cosmic microwave background, the abundance of light elements, the distribution and evolution of galaxies, the large-scale structure of the cosmic web. These observations fit together like pieces of a puzzle, forming a coherent picture of a universe that has been expanding and evolving for 13.8 billion years. But the story is not complete. We do not know what set the initial conditions. We do not know what happened before the Big Bang, or whether before has any meaning. We do not know whether our universe is one of many, a single bubble in an eternal inflation that spawns new universes without end. We do not know the ultimate fate of the cosmos, whether it will expand forever, cool and dilute into a featureless void, or undergo some other transformation we cannot yet imagine. What we do know is that the picture we carry in our heads, the picture of an explosion, a cosmic bomb going off at a particular place and time, is wrong. The reality is stranger and more magnificent. Space itself is expanding. The expansion has no center. The Big Bang happened everywhere, including right here, and we are part of it, not observers looking in from outside, but participants embedded in the very fabric that is unfolding. Cosmology is not finished. We do not know what dark energy is. We do not know whether inflation really happened, or if something else explains the horizon and flatness puzzles. We do not know whether the universe is finite or infinite, whether it is the only one or one of many. We do not know what happened before the Big Bang, or whether that question even makes sense. What we do know is that the universe has been expanding for 13.8 billion years. We know that it began in a hot, dense state radically different from the cosmos we see today. We know that space itself is dynamic, capable of stretching and curving and shaping the motions of matter within it. We know that the Big Bang was not an explosion, and we know that there is more to learn. Every generation of astronomers has pushed the boundaries of the observable universe farther. Hubble showed us that galaxies exist beyond the Milky Way. Penzias and Wilson showed us the afterglow of the early universe. The Hubble Space Telescope, named for the man who discovered cosmic expansion, has revealed galaxies billions of light years away. The James Webb Space Telescope is peering even farther, studying the first galaxies to form after the cosmic dark ages. Gravitational wave observatories like LIGO and Virgo are opening a new window on the cosmos, detecting ripples in space-time from colliding black holes and neutron stars. Future observatories may detect gravitational waves from the inflationary epoch itself, direct evidence of the universe's earliest moments. The story is not over. It is still being written. And you are part of it. You are made of atoms forged in stars, organized by information encoded in molecules, thinking with a brain that evolved over billions of years on a planet orbiting an ordinary star in an ordinary galaxy, in an unimaginably vast and ancient universe that began not with an explosion, but with an expansion that continues to this day, an expansion that includes you. So the next time someone tells you about the Big Bang, about the cosmic explosion that started everything, you will know the truth. There was no explosion. There was no debris. There was no center where it all began. There was only space, stretching, time, unfolding, matter and energy, cooling and clumping, and eventually, after billions of years, becoming aware of themselves. You are that awareness. You are the universe looking at itself. You are the expansion made conscious. The quantum fluctuations become curious. The cosmic background radiation contemplating its own existence. The Big Bang happened everywhere, including right here, including right now, including in you. Remember that the next time you look at the stars. And remember this, the greatest misconception about the origin of the universe is not a failure of knowledge. It is a failure of imagination. We picture explosions because we have seen explosions. We imagine centers because we live on a planet with a center. We think of matter flying through space because that is how things work in our everyday experience. But the universe is not everyday. It is not ordinary. It is not what we expect. It is something stranger, something more subtle, something more wonderful than any explosion could ever be. The Big Bang is real. The explosion is not. And understanding the difference is the first step toward understanding everything. But let me leave you with one more thought, because there is something even more remarkable hiding in this story, something that speaks to the deepest questions we can ask about existence. When Fred Hoyle coined the term Big Bang in 1949, he was trying to ridicule an idea. He was a brilliant scientist, one of the greatest astrophysicists of the 20th century, and he genuinely believed the universe had no beginning. The steady-state theory he championed was elegant and philosophically appealing. An eternal cosmos, always existing, always creating new matter to fill the voids left by expansion. No messy singularities, no inexplicable first moment, just an infinite, self-sustaining universe that had always been and would always be. Hoyle lost that battle. The evidence for the Big Bang became overwhelming. The cosmic microwave background, the abundance of light elements, the evolution of galaxies across cosmic time, all of it pointed to a universe that was once vastly different from what we see today. A universe that was hotter, denser, younger. A universe that had a history. But here is the thing. Hoyle was not entirely wrong to be suspicious. The classical Big Bang singularity, the point of infinite density at time zero, is not a physical prediction. It is a sign that our theory breaks down. General relativity tells us what happens when we extrapolate backward. but it does not tell us that the extrapolation is valid all the way to the beginning. The singularity is not a thing that happened. It is a question mark, a placeholder for physics we do not yet understand. Modern cosmology has moved beyond the naive picture of a universe popping into existence from nothing at a single, well-defined moment. Inflation suggests that whatever the beginning was, it was not the hot Big Bang itself, but something that preceded it, an exponentially expanding vacuum-dominated phase that set the initial conditions for the universe we observe. And inflation itself might be eternal, with new universes constantly bubbling into existence in an endless multiverse. This does not mean the Big Bang is wrong. It means our understanding is deeper. The hot, dense state 13.8 billion years ago was real. The cosmic microwave background is its echo. The expansion of space from that state to the present is measured and confirmed. What we do not know is what came before, or whether before is even a meaningful concept. And this uncertainty is not a weakness of science. It is its greatest strength. Science is honest about what it does not know. It does not pretend to have answers it lacks. It follows the evidence, revises its theories, and keeps asking questions. The question of ultimate origins may never be answered. It may be that the universe has no explanation beyond itself, that existence is simply a brute fact with no deeper cause. Or it may be that our descendants, centuries or millennia from now, will discover physics so profound that it explains not only how the universe began, but why there is anything at all. Either way, the journey continues, and the first step on that journey is to let go of the misconceptions, to see the universe as it actually is rather than as we imagine it to be. The Big Bang was not a bang, it was the universe waking up. Think about that. For the first 380,000 years after the Big Bang, the universe was opaque. Light could not travel freely. If you had somehow been there, you would have seen nothing, just a blinding fog of radiation scattered in every direction by the plasma that filled all of space. There was no darkness, there was no sight, there was only heat and light everywhere, inescapable. Then the universe cooled. Electrons joined with protons. The fog lifted. For the first time, light could travel in straight lines across the cosmos. The universe became transparent. In a very real sense, the universe opened its eyes, and what it saw was itself. The cosmic microwave background is not just ancient light. It is the first light. It is the moment when the universe became visible, when information could flow from one place to another, when the cosmos went from a seething, undifferentiated plasma to something with structure, with form, with the possibility of complexity. From that moment, everything followed. The slight overdensities in the plasma, the quantum fluctuations amplified by inflation, began to collapse under their own gravity. Gas clouds formed. The first stars ignited. Nuclear furnaces burning hydrogen into helium, helium into carbon, carbon into oxygen and silicon and iron. Those stars exploded, scattering their heavy elements into space. New generations of stars formed from the enriched debris, surrounded by disks of dust and gas that coalesced into planets. On at least one of those planets, around at least one of those stars, chemistry became biology. Simple molecules assembled into complex structures capable of reproducing themselves. Evolution shaped those structures over billions of years, producing an astonishing diversity of life. And eventually, one lineage developed brains large enough to wonder where it all came from. This is the story of the universe. Not an explosion, but a blossoming. Not debris scattered through space, but structure emerging from simplicity. Not chaos, but order. Complex, beautiful, improbable order arising from the quantum fluctuations of the early cosmos. And you are part of that order. You are the universe becoming conscious of itself. You are atoms arranged in such a way that they can contemplate atoms. You are the expansion learning to ask questions about the expansion. The Big Bang is not behind you, in some distant past. It is within you, in every atom of your body, in every photon of light that reaches your eyes, in the very fabric of space-time that your thoughts traverse. You are the Big Bang, still happening, still unfolding, still becoming something new. This is not poetry, it is physics. The same laws that govern the expansion of the universe govern the firing of neurons in your brain. The same quantum mechanics that seeded galaxies enables the chemistry of life. The same space-time that has been stretching for 13.8 billion years curves around the mass of your body right now, at this very moment. You are not separate from the cosmos. You are the cosmos. A particular arrangement of it, a temporary pattern in the eternal flux, but the cosmos nonetheless. And the cosmos did not explode into being. It breathed, it stretched, it became, and it is still becoming right now, in you and through you and all around you. The Big Bang is real. The explosion is not. And now you know the difference. Look up tonight. Look at the stars. Each one is a nuclear furnace, burning hydrogen into helium, pouring energy into the void. The light from those stars has traveled for years, sometimes for thousands of years, to reach your eyes. And the space through which that light traveled has been expanding the entire time, stretching the wavelengths ever so slightly, carrying the ancient photons on a cosmic journey from there to here. Now look deeper. Beyond the stars you can see with your naked eye, beyond the planets and moons of our solar system, beyond the 100 billion stars of the Milky Way, beyond the billions of galaxies that fill the observable universe, there is the cosmic microwave background, the oldest light, the first light, the afterglow of the Big Bang, still glowing, still everywhere, still telling us the story of how it all began. That light is 13.8 billion years old. It has been traveling since the universe was a baby, since atoms first formed and the plasma cleared and the cosmos became transparent for the first time. It has seen the birth of the first stars, the formation of the first galaxies, the slow emergence of structure from primordial chaos. And now, tonight, some of those ancient photons are striking the Earth, passing through the atmosphere, entering instruments that can detect them, or simply warming the ground beneath your feet, unnoticed, unregarded, carrying their ancient message to no one in particular. But you know about them now. You know what they are. You know where they came from. And you know that the event they speak of, the Big Bang, was not what you thought it was. It was not an explosion. It was not debris. It was not matter flying through empty space from some primordial detonation. It was space itself, coming into being, time itself, beginning to flow, the universe itself, waking up and starting to become everything it would ever be. You are part of that becoming. You are made of its substance. You carry its history in your bones. The Big Bang is not something that happened to the universe. The Big Bang is the universe, and you are standing in the middle of it, looking up at the stars, wondering where it all came from. Now you know. It came from everywhere. It is still happening, and you are part of it. The explosion never happened, but something far more magnificent did. Space stretched, time unfolded. Quantum fluctuations became galaxies, stardust became life, and life became aware of the cosmos that created it. That is the real story of the Big Bang. That is the truth hiding behind the myth. That is what the universe actually is. Not an explosion, an awakening. And it is happening still, right here, right now, in you. The Big Bang is real, but the explosion never was. And that makes all the difference in the universe, in the cosmos that had no explosion, in the universe that had no center, in the reality that is stranger, more beautiful, and more magnificent than any myth we ever invented to explain it. This is the universe. This is your home. This is the truth. Welcome to the real Big Bang, the one without the explosion, the one that is you.